So it's in the recording. What did I say last day? I said we can go through questions from the practice test if you have any. Let's see here. I posted the solutions, of course. Not of course, it took me a day. I posted the practice test. And so we've got this list of core concepts of things that could be on the test. And so, and the section where it came from. Okay. And so these are all the things, 2 pages, that I expect you to be able to do, right? Basically a list of all the things that we did, okay? And then I have a curated practice test, right? Just like practice test 1, if you are able to do the practice test, then you should feel pretty good heading into the test. Now, what I always caution is that you don't start with a practice test, and I'm guilty of that too, right? You just kind of, you work through the practice test and you try to figure out, okay, what do I need to learn? But what I would prefer that you do, or kind of suggest that you do, is study these concepts first and then use the practice test as kind of a dry run, okay? A wet run? I don't know, a first run. And so, because then you'll actually be able to see kind of where you're at. Otherwise, it's really difficult to figure out where you're at. Now, I also posted this mom assignment, this practice for test 2, which is not for marks. I can't click on it because when I'm as a student, it bungles everything. So I can't click on it, but it's not for marks, but it is just more of the same practice problems. So maybe try those ones first and then sit down and do the practice test.
Those like the 7 videos and stuff too.
Yeah, they're just the same as the assignment questions, but kind of in a condensed, curated way. Yeah. And then in case you missed it, we've got our test on Tuesday, of course. And like I said, we're going to start circles today, unless you have questions about the practice test. But I think it's pretty self-explanatory. Solutions. I just wrote them out. Oh, good question. Where is it? I need to post it. I need to post the formula sheet. You'll get a formula sheet. There's really no formula that I think that we've used that I'm not going to give you. So it's not a concern. For example, in this practice, I included the finding the vertex of a quadratic. That'll be on your formula sheet. So if there's kind of things like that, that'll be on your formula sheet. But pretty much, but you need to know when to use it and how to use it. Yeah. That's the pickle, ain't it? All right. So let's just do a quick kind of, you have to describe the long run behavior of a polynomial. Okay. You have to kind of show me that you understand some basic terminology, things like the degree and the leading coefficient and maximum number of real zeros. Interesting. And yeah. So it's going to be the highest power of x. Yeah. Let me go in here so I can. Is that the door?
Yes.
But there's no one.
Tim went there, I think he's gonna be right back.
Maybe you went to the walkthrough?
It's gonna make us listen to the loud hallway. Okay, let's see here. There. Okay. Now I can use my pointer. Yeah. I give you a quadratic. You have to find some B and C that given some vertex, right? And so you need to solve for B and C, and you use this formula here. Word problem. Things that use what, a quadratic again. We spent a lot of time on quadratics, so there's a lot of quadratics on the test, of course, and same with exponents and logs later. And I do them kind of chronologically because otherwise I find that it gets kind of confusing. I was like, is that the door? But then there was no one there. I'll close the door. And so a quadratic, right? Just kind of the anatomy of a quadratic, knowing how it flips and behaves, but also the quadratic formula, right? And so let's see here. Same formula, I think. So that one's useful. Quadratic formula to find the zeros or the roots. The domain of a function, right? We've talked about domain in terms of fractions, right? We can't divide by 0. Roots, we can't take the even root of a negative number. And then logs, right? We can only take the log of a positive non-zero number, right? Then I give you another polynomial. This one's factored. I want you to describe the long run behavior again.
We go over that one.
This one here?
Yeah.
Yeah, you bet. Can we just talk through this? The solutions. Okay, so if I have, okay, if it's all muddled, here, I'll add this in again, but let's start here. So if I were to expand this, right, we're looking for the highest power of t, okay? And so I would get t and then multiplied by t, but t squared, right? So here I get a t squared plus a bunch of numbers, right? Question?
No, I was just.
Oh, just
Yeah.
doing the dance, the polynomial dance.
Yeah, thinking which way it goes.
Nice. So this is t squared. And this is t swift. No, t squared. Again, right? Once I expand this in. But then if I'm multiplying these things, and I don't want you to expand these, right? The skill is to kind of look for the highest, right? We're looking for the degree, because that's going to tell us what the end behavior looks like, right? The long run behavior. And so this, we could call this the, the end behavior, or end behavior. You could call it the long run behavior on the assignments, so that's why I kept it as long run, but you can call it end behavior if you want. So now I'm looking for the highest power of t. And so if I expand this here, bless you, then I get t times t squared times t squared. Okay. So then this is just t to the 1, of course. So t to the 1 times t squared is going to be your highest power. And this is where we need to be able to multiply bases, same bases. And so I get t to the 1 plus 2 plus 2 is t to the 5, which means I have the highest power in there, once I've expanded it all out, would be 5. And so that's how you kind of snag those highest powers. Then we have a reflection here. Ugh. Reflection. So an odd power, right? Any odd power behaves like the blue line, right? But with the negative out front, the reflection becomes like this, right? And so here, this is the odd power. And let me just match the colors here. I'll just redraw it. Because then the reflection is going to do something like this. I'll still highlight it. So then the end behavior looks like this. So t is on the x-axis, or the t-axis, I guess, right? And so now we can describe this end behavior, because as t goes to positive infinity, right, the function of t is going to go to negative infinity. And as t goes to negative infinity, the function itself goes to positive infinity. And how we write those, right, as t goes to negative infinity, f of t goes to positive infinity, right, that's up like that. And as t goes to positive infinity, then f of t goes to negative infinity. So it's been a while. So worth reviewing those, right? Going back to the toolkit functions, knowing the shapes of these animals is going to help. I had a prof one time, and he would always speak really quietly. And it took me about half a term to figure out that he was just saying animals. It's like, oh, this animal here, this animal here, this animal here. But he was just referring to the variables. So they were all little animals. But I did not, it's like, what is he saying? What is he saying? I don't understand. But an odd function is one animal. A reflection is just a reflection of that animal, I guess, by that logic. Does that clarify? Cool. Long division of polynomials. If you prefer to do synthetic division, that's totally fine. Right, I don't specify, you just have to find the quotient and the remainder. Oh, I guess I do specify, but I'll say using long division or synthetic division if you prefer. But we only covered long division. Synthetic division's in the textbook, but so I'm kind of expecting to see long division, but totally fine if you use synthetic, because if you know it already, then that's cool. So we have to find the quotient and the remainder, which involves remembering what those are, right? And so, but also remembering the process of the polynomial long division, right? That's all we're gonna do. So we did talk about the factor and the remainder theorem, which you can use to check your work, right? The remainder theorem says that, okay, if I have x minus c and I plug in c, I should find that it becomes the remainder. So you can use that to check your work, but I'm not going to test you on it. Okay? So just this from section 3.7, I think. Okay. I give you a rational function. I guess this is also from, is it 3.7? Sometimes I switch up the order because if the spacing gets weird, but only a little bit. Maybe this is 3.4, I can't remember. These functions are going to be whoa, hello? Is that me or? It's in the speakers, in the computer. I'll just mute everyone. There we go. Unless you had something to say. You can unmute yourself. So two different versions of the function. This is to make it easier for you, okay? And so depending on what you want to do, right, that'll determine which version of this function you'll want to use, right? Sometimes, pardon? Yeah, this one's just the factored version of this one, right? And you can expand this out to check, but they should be the same. Okay. And so you have to find the domain. Okay. That should be, relatively easy. What's the y-intercept? That's where x is 0. Again, relatively easy. Doesn't matter to me. I like to do this one for finding the y-intercepts, just because I find that it's a little bit easier, but it's up to you. The x-intercepts, you have to find where the function is equal to 0, right? The x-intercept is where y is equal to 0, or f of x is equal to 0. So then you need to figure out, when does this thing equal 0? We know we can't divide by 0. So the only way this can be 0 is if the numerator is 0. So then you figure out, okay, well, when can the numerator be 0? There's going to be 2 times where the numerator is 0, right? Which, if you prefer, right? If you prefer, you could use the quadratic, right? And use the quadratic formula to find when, what values of x make that 0, right? So I like this one, but the quadratic's a sure thing, right? And so you can use either or. Vertical asymptotes. There's going to be a vertical asymptote at the point that's not in the domain, right? It can't happen at that vertical asymptote, and so that's how it's excluded from the domain. But it does involve remembering what a vertical asymptote is. I'm not going to check your horizontal asymptotes, so don't worry about that. But I will check your vertical asymptotes. On the vertical asymptotes? Yeah. So the vertical asymptote, what we said was, okay, in the denominator here, 2x minus 1, we know it can't be 0 because that's not possible. We're not allowed to divide by 0. So then for the domain, what we said was, okay, 2x minus 1 can't be 0, which means 2x can't be 1, which means x can't be 1/2. That tells me that in the graph, I have some sort of, I'm trying not to say asymptote, some sort of a glitch in the matrix, I guess, a glitch in the graph, which is going to be a vertical asymptote. And so that's why the vertical asymptote is at x equals 1/2. Should probably just be one point, but I don't know, being generous, I guess. Sometimes I overweight some of the easy questions, bump your grades up. I'm gonna keep it that way. Whew, how's that for a rational function? So now we want to list all the values of x where there's a vertical asymptote. So here it is again. But what do you want to do? what you're gonna do is you're gonna say, okay, I've got x minus 1 and x minus 1, x minus 4 and x minus 4, x minus 6 and x minus 6, x minus 7, x minus 7. So what we're gonna do is we're going to cancel as much as we can, right? And so 6 minus 2 makes 4, and so this guy is gonna go away, and so that's what's happening here, right? 2 minus 1, right? Really what I'm doing is I'm floating this x minus 4 to the top and using that same base to combine the powers of 2 and negative 1 to make just 1. Notice I only crossed out the 2, which implies that there's a 1 here, but maybe I should write it. Okay. Now these are going to be gone. Okay. X minus 6 to the 6 times x minus 6 to the 1, float it up to the top, so that's a negative 1, so that makes 5, and then cancel the x minus 7. Now, because these are all canceled here, I'm left with nothing in the denominator, and so that tells me that there are no vertical asymptotes in this case. What do we have, though? That means there's going to be holes at those places. Right? Once they cancel, they still are there in the background, right? We can morph it into this new function, but the original function was this, right? We did divide by these things. And so now at x equals 1, x equals 4, x equals 6, and x equals 7, we still can't have those values because they were in the denominator originally, right? And so that's what makes them holes, is when I'm able to cancel them. So they're not vertical asymptotes unless there's something left here, right? There could be something where it doesn't cancel. Let's say, for example, let's pretend that this little guy, this x minus 7 didn't cancel. Let's just ignore this guy. Then I would have a vertical asymptote at x equals 7, right? Because if I let x equal 7, x minus 7 makes 0. So then I'd be dividing by 0. But list all the values of x where there's a hole in the graph. And then explain. You have to tell me why, right? You have to explain for both of these. And that's why it's 2 marks. All right. The fox population. So here we have exponential growth. We're getting into our exponential functions here. So that's chapter 4. And so first things first, this is kind of more fresh, right? We've got an annual growth rate of 8% per year, which tells me I have to use this version of the formula, right? You can convert this to b if you want, a b to the t, but might be easier to use this version, which you'll have on your formula sheet. So you can develop the function, right? You can use the function to make an estimate, right? Plugging in some value into x or t. Do you remember doing this? Finding the formula for an exponential function that passes through 2 points? Well, you will. So you've got 2 points in this function. And so here, x is 2. So when x is 2, f of x is 36. When x is negative 2, f of x is 4/9. So what you're going to do is you're going to first solve for probably a, and then plug it in and solve for b using the second point. Keeping in mind the domain of b, right? B can't be negative. Okay. B between 0 and 1 means there's decay, and then B greater than 1 means there's growth. Right? But we can't have a negative B. And so you're gonna just land on one value. Nice. Some of these, just to set you on the right path, give you the formula. So we've got a compound interest question. You invest some amount at some rate, and you want to figure out how much is in the account after some amount of time. Better make sure that it's positive or greater than what you started with. Otherwise, it's a really bad investment. I make you practice with annually, quarterly, monthly, playing around with these Ks, right? In the formula, you've got this K, which is the compounding frequency. Are they watching a movie again? We're gonna watch a movie one day.
I still want to turn the volume up so we can hear it too.
They should just share it to our screen too.
Last week.
We'll watch Moneyball or something. I still haven't even seen it, but that's like that's a stats movie, right?
Oh wait.
Huh?
That was Jonah Hill, right? Yeah. But
Isn't it Brad Pitt?
or yeah.
Yeah, right?
Jonah Hill is a secondary
Mm, love Jonah Hill. Compounding continuously is different. Anytime we have continuous growth, we have e to the kt. So that's the only sneaky one. Then, because I won't print them in color, even though that would be nice, I labeled the graphs. So they have names: green, red, orange, blue. And so what you want to do is you have to match each equation to the graph, relying on what two facts? Each graph is going to pass through 0a, and so that's how you're going to find what a is. You figure out, so at x equals 0, you can find a, and at 1ab, but if you know what a is from 0, right, then you can figure out what b is, and then you can kind of plug away at it. These should really just be 1 point, because they're little itty bitties. Write the equation in exponential form. N to the z is equal to w. Right? Or write the equation in logarithmic form from exponential form. This one I find is a little bit trickier because you have a base of 5, okay? And then I just kind of imagine the 5 to the q is equal to v. So I still imagine that kind of loop, but in reverse. I guess you could kind of drop them off in reverse, but my brain doesn't work that way. And then evaluate each of these. I want them in exact form, right? So √4, because e to the log or natural log of √4 is just √4. Again, quick wins here. Solve an exponential function. So we've got t in the exponent, which means that I need to isolate the exponent by dividing both sides by 1,000. And then I need to take some log. You could take the log base 1.03, but that's kind of weird. This is a typo actually. It's not the natural log, it's the log base 1.03. So used to just the natural log. I use the natural log, of course, but it doesn't matter. You'll find it's the same answer. Okay. So then once you've taken the log, any log here, then you can bring that exponent downstairs and then you'll be able to solve for t.
Go back up.
Yeah.
For D there, am I able to plug in the calculator to get that? So, like, send it over.
You can. You're allowed to. It's just one mark. You can use your calculator. How's that for a rule? Log laws, right, as a single logarithm, right? So take some log function like this. They'll have the same base. Well, you have to check that they have the same base, but they will. And then you need to combine them and write as a single log with a coefficient of 0, which means if you have anything out front, you need to float it to the exponent, right? Nice. Solve for x when the x is in the exponent on both sides. It looks tricky, but if the exponent's on both sides, then you can take the log of both sides, which you would be doing anyways, right? And then that would bring the exponent downstairs, and then you'll be able to kind of rearrange and cross multiply to find eventually x. So you do need to kind of rearrange some stuff, but eventually you'll be able to get all your x's on one side and everything else on the other side. And it'll be kind of nasty, and if you want, you can leave it in exact form. And if you don't want to write this as log base 3 of 6, right? That's using the change of base formula. Okay. I just did that because I was being lazy. You can keep the natural log of 6 over the natural log of 3. Again, it's just a number, so it doesn't matter.
Are we giving all those little log rules on the?
Yeah.
Oh, good. Wow.
I know. Aren't I so aren't I so nice?
So nice.
I'll give them to you.
Don't complain. Don't complain about what?
Let's see here. Log. Oh, solve for x. What do you see almost immediately? Probably, maybe, hopefully. You will see once you've worked on it, right? Once you combine these, because how do you solve for an x inside the log? I need to raise it to the base of the log, but I can't do that if I have two separate logs. So step number 1 would be combining those logs. But when I do, ruh-roh, I get a quadratic inside. Ah, dang it. All right. But then once I have one log, I can raise it to the power of 10 or 10 to the power of the log, but do it to both sides, right? You have to do it to both sides, but then the equality stays. Then I'm left with a quadratic, right? I can float this over to the other side and set it equal to 0, right? Because in order to use the quadratic formula, which I'll give you, of course, it needs to be equal to 0, right? Because we need to find what values of x make it 0. And so for it to work, you have to set it equal to 0, which you can just do by subtracting 1000 from both sides. Your calculator does do your quadratic formula, but I can't remember how to do it. But it might be worth a Google, because the quadratic formula here takes you all the way to here. Now, I'm fine if you tell me that, hey, this is what I'm about to do, and here are the values that I would put in, and then just write a note, use my calculator to find these values. I'm fine with that, right? I don't actually care how you find the values. Just show me that you know to use the quadratic formula and what work you would be doing, and then how you got there in the end. I don't care.
Just from that point, just the answer right after that. -2 +.
Yeah, except, but wait, there's more. We can't take the log of a negative. So anytime you get a negative value, then it's not a solution, right? And so there's only going to be one solution, and that's when x is 29.69 in this case. Whew. I've rounded, and that's fine. You're allowed to do that. But I didn't round until the very, very end, right? Okay. Nice. Newton's law of cooling. That's a fun one. And I've even made a note that you guys want the dead body one. Even though
I feel like it's a nice way to brighten up the morning.
yeah, you guys are so dark. I like the cheesecake one. How long until you can eat it?
Cheesecake's dessert, that's like after dinner. You barely
Yeah,
breakfast.
murders for mornings.
Yeah.
You can hear it in the name. Yeah, terrible. So it's not because I wanted to. You guys said you wanted the murder one, the dead body one. But these, we did these just the other day. First thing you're going to want to do is figure out the information that you're given, and then you need to solve for A first, is usually your first stop. Okay? And then you use that A and the second point, the second time point, and you solve for K, and you're allowed to just keep a few decimal places until you run out of interest, right? And so here, things stop being interesting after the 6. So I've decided to keep 5 decimal places. And in general, you want to keep at least 4 or 5. Right? Because K is going to be very small. And so, but then you are allowed to use a rounded value because you have to write it out all this time. So, you can store it and just write a shortened version, but and then we want to find what time point is this thing ready to eat. Let's solve for t, which is going to be an exponential function with the function that you built. And an earthquake one. The earthquake ones can be tricky, but I promise it's going to be just like this. Just different moments of magnitude. So different values of m. Okay. But that's about it. So the only thing I'm going to change is this. So as long as you're able to rework it, right? So here, one earthquake has a magnitude of 3.4. If a second earthquake has 4 times as much earth movement, okay, fine. I guess that one can change too. Just to keep things interesting. Right. First, what you're going to do is you're going to figure out what the S is for the first earthquake, because you know what the M is for the first earthquake. And so you can solve for S, right? You've got it inside a log, so you need to raise it to the same base. And then you'll be able to find S. Now, in this case, I've kept it just times S naught. S naught is 10 to the 16, so if you want to plug that in, you can, but it's going to cancel pretty quick anyways. So then I just left it as S naught. Because then for the second earthquake, I want to solve where the S for the second earthquake was 4 times the first one, the first S, I should say. And so now, right, but this S here is this. Maybe I should put a little 1 there.
Is that a S1 over 10 or 51 over 10?
Yeah, it's 5.1 because it's 5.1 here. But then if I put in 4 times S1, but S1 is 10 to the 5.1 times S naught, then I get 4 times 10 to the 5.1 times S naught divided by S naught. So those will cancel. And I'm left with 2 over 3 times the log base 10 of 4 times 10 to the 5.1, putting me at a magnitude of roughly 3.8. It's just part of the formula,
Oh,
that one here.
you
For
put
M.
that back to the second.
Yeah, so the procedure will be this. Maybe I'll call this S1 throughout. Solve for S1 using M1, which was 3.4. I'll do that. So then here, you've got to that point. Now use S1 to solve now use S1 in S2 is equal to 4 times S1 to solve for M2. So many arrows. I'll post these kind of updated solutions for you. That's a glitch.
Yeah, so for the 51 over 10, that's my calculation, that being 51 over 10. How do we get to 5.1?
51 over 10 is 5.1. Then 5.1 is being raised to the base. So 10 to the power of 5.1.
But the 5.1, doesn't that come from 3.4 divided by 30?
Well, yeah, that's what I'm getting. I'm getting it as my calculation. I'm getting 51 over 10, not 5.1.
It's not the same thing, though.
Yeah.
51 divided by 10 is 5.1.
Oh, yeah. that's-
Yeah.
that makes sense.
You can convert it to the decimal version and it should be 5.1.
Yeah, that's
Yeah.
Yeah.
The engineering calculators always give you exact answers, those guys.
Just defaults the fraction. It's really.
Yeah, try to get bugs me.
I think you can change the setting, but
I have it when you give me decimals right away.
I don't know how.
Either at this point, it's now the button I press. Now, like I just press it when I hit equals or something.
I only press it when I'm curious.
I don't use the fractions. I'm sure it's more useful when you're doing specifically math and it gets like the huge numbers, but because the numbers we use are never that bad, it's just like an extra step that's really annoying.
And usually if I'm doing actual calculations, I just store all my values. So I don't really pay attention to what they are. Does that make sense? A LaTeX flop. Page 12 out of 10. Because I had to compile it. Usually you have to compile it like 3 times, but I only compiled it once, I guess, for it to take effect. But that's it. Can you pull that off? I think yes.
A lot of confidence there.
You'll have questions that you like. You'll have questions that you know you don't like. I would suggest maybe kind of doing the ones you like first so that you're not stuck at the end trying to wrap up ones that you actually know how to solve, right? So, but I guess that's your choice, your test, your choice. Let's see here. I'm gonna rename this file so I remember that this was from class. Hopefully that's what it says.
And we have this sheet on Moodle.
Uh-huh. Okay. Nice. All right. You ready to tune out because it's not on the test? Or what should we do? I do want to do some circles. There's a really fun problem that we're gonna do, but it's not for a little bit. We need a couple more skills or review a couple more skills. I think you've got them already. Frank keeps asking me, have you done trig yet? Like, no, not until the end. You know that. Frank. No, I hate trig. I do. I shouldn't say that. I just need to work at it more and then I'll like it, but ugh. What trig have you used? Like SOHCAHTOA stuff?
Yeah, but only SOHCAHTOA, not the other ones.
Yeah, okay. SOHCAHTOA, big player. Not today. No SOHCAHTOA today. But I guess not until Thursday. But you'll be pros already. All right. Chapter 5. Oh, question, comment, concern.
No, so many concerns. Nothing to do with this.
Any questions about the test before we jump in? Huh?
Yeah, I really need one of those two to make up for the last one. At least 90. I'll go down to 90.
settle on 8.
Yeah.
Yeah. I'll settle on
Okay. This bargaining is really easy for me. You've just talked yourself down. Yeah. The power of just staying quiet. Yeah. Can I have 100? Oh, okay, 90. How about 80? Keep going. Yeah. All right. So we're not going to go crazy on trigonometry, but there are some things and kind of key skills that we're going to work on now as we're kind of wrapping up the course. It feels like I guess we are. But let's do. So section 5.1 is on circles. Now I'm not going to do everything in all these sections. I've kind of got a select couple of skills that we're going to work on. And so if you're reading the textbook, there might be things that are interesting, but that I'm not going to test you on, for example.
Your assignments online just based on what you want us to learn.
Yeah. Yeah. Okay. They came, so they're from the author, but then I went through and I go through and I exclude the ones that I don't want you to do. All right, Pythagorean theorem. That's a fun one. Might remember. right? If you have a right triangle, meaning what? Meaning you've got this 90-degree angle here. This is a right triangle. It's an obtuse. Which I think is a synonym for wrong.
Yes.
Yes. The sum of the squares of the legs, which would be not the hypotenuse, I guess, is going to equal the square of the hypotenuse of the triangle. So just a couple of kind of refreshers here. But usually I find that, yeah, people tend to remember what the hypotenuse is. And so it's always the longest side, but also the one that's on the angle and opposite the right angle. And so a squared plus b squared equals c squared, which if you have two of those, you can solve for the third. Now, what if we have something like this? Now we're going to be working on a coordinate grid here. Kind of approximately. Usually what I do is I figure out, okay, so my x's are going to run from -5 to 1, and my y's are going to run, I need space for at least 2 to 4, right? And so just kind of giving myself enough space here. 1, 2, or maybe I make it a little bit loftier here. 1, 2, 3, 4, 5, whoop, keeps going. This is just a sketch to see what's going on here. And 1, 2, 3, 4, 5. Not very good because my spacing is really bad. Oh, I always forget. These are trending. It's not snowing though. It was the other day. I interrupted my test so I could tell them that it was snowing. It was so important. It's a good day. Check it out. How beautiful is that? I know. And also, check this out. How cute.
It's very useful for tests.
Right? And later, we'll use this.
Cool.
Rude. I know. Oops. Yeah.
Unfortunately, when I took grade 12 math here, I decided not to study it until the last 2 weeks, and then I crammed it all in for the exam. I got 70% on that. Yeah, I didn't remember anything. It was been like this last year.
Math prof went a long time ago. He called me Corey the procrastinator. As a example.
Yeah.
I had only done up to like chapter 2 or 3, like 7. And I did do geometry trick, and there's lots of 2 weeks left. So I had to do all of those.
Right,
I was like a test day.
yeah, it wasn't fun. It was a very bad couple of weeks. Gained absolutely nothing from it.
Got 2 points. You can plot them. Soon. So now we're working up to it. So now the distance between these two, let's call the distance D. You can call it C if you want, but I think D makes more sense for distance. But you can draw this out as a right triangle. Right? And so here, this little guy and this little guy. Oh. Of course, don't pay attention to my poor, there. So now, what would you do? If you had to find this distance, you can find A and B. Doesn't matter which ones you call A and B. We can say that this maybe is A and maybe this is B. Or vice versa, doesn't matter. So we need to find A, and A is the rise essentially, right? The rise from a y value of 4 down to a y value of 2. So A is going to be 2. Keeping in mind the distance between a negative number and a positive number, right? You want to go -5 and then -1, but the distance is always positive. So then you take the absolute value, or you can just, in this case, you can look and say, okay, from 1 to -5, okay, I have a distance here of 6. So then if A squared plus B squared equals D squared, in this case, C is equal to D, or the hypotenuse is always on the other side of the equal sign. So then I have 2 squared plus 6 squared is D squared. And this D keeps looking like a 2, but it's not. Maybe D was a bad choice. 36 plus 4, I think. 2 squared plus 6 squared. (40) is D squared. So D is the square root of 40. Now, if you take the square root of 40, you get 2 root 10. So you can write it as 2 root 10 or root 40. It doesn't matter to me. Right? But the distance between these two is root 40, which is a number. Right? The square root of 40 is roughly 6.32455, which checks out. Or D is roughly 6.324555532. Why does it check out? Because it has to be the longest distance because it's the hypotenuse, right? And so here I've got a distance of 2, and here I've got a distance of 6, and here I have 6.32, let's call it. So that checks out. All right. So then we can generalize this and we can say, well, what if I want to find the distance between any 2 points, x1, y1 and x2, y2? Then we can just rearrange our formula, right? Because A here is, let's see here, y2 minus y1. Let's see here. This distance is y2 minus y1. y2 is 4 and y1 is 2. And here, this distance is x2 minus x1. x2 minus x1 would be -5, 1 minus -5. There we go. 1 minus -5 is 6. Good. So we can generalize from x1, y1 to x2, y2 as x2 minus x1, square that, right? Because up here, this is what we called b, and this is what we called a earlier. But solving for the distance d, we had to take the square root, and that's it. So what if we have to find, so here's an example, find the distance of r. And yes, I did white out the circle that goes around here. So I want to start nice and slow. Okay. All right. So what I want to do, or what we are going to do, is call these points. All right, I've got some x, y, and I've got some hk. Let's call, now usually how we label the points, it doesn't actually matter because when we square a distance, it becomes positive anyways. And so it doesn't really matter which one you call x1, y1, and x2, y2. But for my preference, I like to label this as 0.1 and this as 0.2, just kind of the order that they appear from left to right. So I'm going to call this x1, y1, and this is x2, y2. R is the distance that I'm trying to find. So if I apply the distance formula, R is the square root, and I'm going to write the general formula here of x squared minus x1 squared plus y2 minus y1 squared, and then square root it. So now R mapping x2 and x1 and y2 and y1 from these points just into the formula. As long as you kind of hover above it and stay on top of it, it's okay. X2, we call it X here. X1, we called it H here. So X minus H squared plus Y2 is Y, and Y1, we called it K here. Y minus K squared. We don't know what that distance is because we don't have any values for those points, but in general, that would be the distance, right? But from HK to XY, or if you prefer, R squared, right? You've got a square root on this side, so to undo the square root, you can square both sides. So you get R squared is going to be X minus H squared plus Y minus K squared. Drum roll for the equation of a circle. That wasn't, was it a drum roll? No. Too fast. So here, the equation of a circle centered, try not to read it all in one go, at the point HK. And so now we've got a generic HK with some radius R is going to have this equation for the circle. Now, what does the equation of the circle do? It'll give you all the values swinging around this rope, right? R. We call it an equation, right? Because it's not a function, right? It doesn't pass the vertical line test, right? And so it's not a function, but it is an equation. We can still work with an equation, right? Because it has an equal sign in it. It's an equation. Yeah. And so I don't remember what I was going to write here, but clearly I wanted to leave room for something. Could it have been, sorry, just close your eyes. Okay, I think I remember what it was. If we let the circle be centered at the origin, if the circle is centered at the origin, 0, 0. Wait, hey. Well, 0, 0 would be taking the place of HK then. So where you see an H, you're going to write 0, and where you see a K, you see 0. Then you get this special case where R squared is X minus 0 squared plus Y minus 0 squared. That is what I wanted to say here. Just need one more line here. So then R squared is X squared plus Y squared, which might sound familiar, but that's just a special case where it's centered at the origin. But in general, right, you can have it centered at HK. Okay, nice. Oh, how do you guys like seeing my toolkit here? I think it makes more sense so that you can kind of see what's happening. Finally figured out how to change it. Settings. But it does, I'm so used to you guys not seeing this, so I might block it sometimes. So my apologies. All right, start nice and slow. Write an equation for a circle with its center at 2, -3, and a radius of 5. Okay, we need the equation of a circle. R squared is X minus H squared plus Y minus K squared. I always like to remind myself which one is the H and which one is the K, and kind of highlight all the things that I've been given. R is 5 squared. R squared is 5 squared. X minus H, and H is 2, so X minus 2 squared plus Y minus K. So I'm going to be really careful and write minus and then -3 in brackets, just so I don't forget that negative on the 3, because what happens? That would be Y plus 3 squared. Right? 5 squared is 25. And I get X minus 2 squared plus Y plus 3 squared. Yeah. So that's the equation of the circle. Now you can plug in any value of X, right, within the range of the circle, right, within the radius of 5 from the center of 2, -3, and you can figure out what the value of Y is, or vice versa. Let's graph this in Desmos to see to make sure that we did it right. And I'll do x minus 2 squared plus y plus 3 bracket squared is equal to 25. Gives us all these points. Maybe that's too many. But it looks like it's centered at 2, -3, so that's good. And it looks like we have a radius of 5. I'm going, hey, sorry, that was loud. Keep you on your toes. Whee. Come on. Crop top. So if we draw 1, 2, 3, 4, 5, 2, 1, 2, 3, -3. Then I have 1, 2, 3, 4, 5. A radius of 5 looks good. Whoa. Okay, weird. How do you think, what would you do if you had to find these points, for example, right? The x-intercepts.
So y 0.
Nice. Totally. I'm gonna just clean this up a little bit. And what color haven't I used here? Find the y-intercepts, sorry, the x-intercepts. I guess we could find the y-intercepts as well, but I drew the x-intercepts, so. But the same method would apply. We see that there will be 2 answers, right? And so then, okay, that is fair. We've got a square in there. We're no strangers to the quadratic, right? And so let's see what we can do here. This is when, so the x-intercept is when y is equal to 0. And so in 25 is equal to x minus 2 squared plus y plus 3 squared. We're going to let y be 0. So then I get 25 is x minus 2 squared plus just 0 plus 3, but I'm going to write 3 squared. Which is 9. Now you got a couple of options here. You see a quadratic, and maybe you just want to use the quadratic formula, which would mean expanding x minus 2 squared, which is fine, right? And then setting it all equal to 0 by bringing over the 25. Okay? You can do that. Okay? But let's just try it without using the quadratic formula. I'll make a note here though. Could use the quadratic formula here. Would require a little bit of work, but you can try it just for practice. So now instead, I'm going to isolate my x minus 2 squared by taking 25 minus 9. 25 minus 9 is what? (16) is x minus 2 squared. I have to take the square root, remembering that the way that we get two answers is when I take the square root, I get the positive version and the negative version. And so here, to remove this square to get at the x minus 2 in here, I have to take the square root of 16, but I need to take the plus minus square root of 16. Is going to be x minus 2. Now, the reason for the plus minus is if you were to square the negative square root of 16, you would get to 16. If you square the positive square root of 16, you get 16. And so either way, you're going to end up at 16, right? When you square it or kind of square it back up. And so that's why you have to have the plus and the negative on there. And I always forget it. The square root of 16 is nice. It's 4. So we get plus minus 4 is x minus 2, which means that x is going to be 2 plus minus 4, right? Adding 2 to both sides. I like to do 2 minus 4 because it's on the lower end first, even though the plus is above and it kind of throws people off. But I get x is either at 2 minus 4, which is negative 2, or x is at, I guess, and x is at 2 plus 4, which is at 6. Which, dun 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 dun, negative 2 and 6. Could have used the quadratic formula. This ends up looking like the quadratic formula. I'd say kind of did, but not officially. For practice, should we use the quadratic formula alongside here? Let's do it. I'll go with orange. Aren't you glad? Okay. I'm just gonna do it kind of here on the sly. I'll make a little divider. Let's see if I can pull it off. Okay. Can I do a sped up version? X minus 2 squared is x minus 2 times x minus 2. And I'm going to force it equal to 0 by taking 9 minus 25. Kind of setting it equal to 0 to be able to use the quadratic formula, just getting that out of the way. And then 0 stays the same here. And so when I expand x minus 2 times x minus 2, I get x squared minus 2x minus 2x plus 4 minus 16. I get 0 is x squared minus 4x, collecting like terms, minus 12. Now I have it as a quadratic. A is 1, B is negative 4, and C is negative 12. And so I get x is equal to negative b plus minus the square root of b squared minus 4ac over 2a. Use your calculator if you know how. Negative b is -4, which is 4, plus minus the square root of -4 squared. I'll write it out. Minus 4 times a, which is 1, times c, which is -12. Divided by 2 times 1. I get 4 plus minus the square root of 16 minus 4 times -12, which is 48. So I get 16 plus 48 in the root. Square root of 64 is 8. An accelerated version. 4 plus minus 8 divided by 2. 4 minus 8 is -4 divided by 2. X is -2. 4 plus 8, 12 divided by 2 is 6. Whee! Choose your own adventure. Whichever one you prefer. We're so used to working with quadratics that I wouldn't blame you for wanting to use the quadratic formula. I find that it just kind of makes it more mindless, which is a good thing for me. I don't know about you guys. Okay. Any questions about that one? So far, circles are not too bad. Then I put all these examples on because otherwise it would just be a ton of blank pages. So we're gonna add pages for work here. In fact, I'm gonna add a page here. Ooh. And I'm gonna bump this up. Reverse it. If we have a circle, what are some key things you need to have before you can write the equation of the circle? You need the center and you need the radius. Right? So looking at this thing, let's see here. I've got a center, looks like it's here. The center looks to be at -2, 1. That's important. The radius looks like it's 2 all around. Otherwise, it's not a circle. Okay. Now, remember that r squared is x minus h squared plus y minus k squared. Okay. Two squared. Now it's just a matter of plug and chug. 2 squared times x minus -2 squared plus y minus 1 squared. I just want to check something. Okay. So I get 4 is x minus -2 is x plus 4, oops, squared plus y minus 1 squared. How about, oh, sorry.
Why did that turn out 4?
It didn't. Turned into a 2. Sorry about that. Thank you. Did not turn into a 4. I know what I did though. 2 squared. What if we had to rewrite this in the format that we're used to, right? F of x is equal to some function of x, or y is equal to some function of x. And so we can rewrite this as y is equal to something by solving for y, rearranging just for y. What would I need to do? I would have to, if I'm trying to solve for y, I need to isolate this y minus 1 squared by subtracting x plus 2 squared to the other side. So I can say 4 minus x plus 2 squared is y minus 1 squared. I'm going to leave it as x plus 2 squared. You could expand it out if you want to, but it's almost cleaner to just leave it as it is. Because then what are we going to do? We're going to take the square root of both sides. But when we take the square root, I get the plus minus square root of 4 minus x plus 2 squared is y minus 1. You need this plus minus. Why? Because if x is -1, for example, there are 2 values for y. One of them is going to come from the negative version of this square root, and the other one is going to come from the positive version of the square root. So you need that plus minus, otherwise you would just be finding 1 point. Then I want to solve for y. So first thing, I'm going to kind of revolving door this, and I'm going to say y is going to be, and it doesn't really matter. You can add 1 at the tail end of the square root, just being really careful that you don't put it inside the square root. So just to avoid that, I'm going to add 1 to the front instead. But I'll rewrite what I just said first. 4 minus x plus 2 squared. And then I cap my root and then add 1. You can leave it like that, or you can write y is 1 plus minus the square root of 4 minus x plus 2 squared, if you prefer. Otherwise, I find that this could get lumped into the square root, which would be wrong. So let's try it. Find y at, let's do -1. It's not easy to see what the y values would be. Let's see here, copy. Crop this up here. What if we have to find y at x equals -1? So here we are at x equals -1. I've got a point here and I've got a point here. We know that y is 1 plus minus the root of 4 minus x plus 2 squared. -1 for x. I get y is 1 plus minus the root of 4 minus -1 plus 2 squared. Negative 1 plus 2 is 1. 1 squared is 1. 4 minus 1 is 3. So 1 plus minus the root of 3. Which puts me at, of course, the exact answer would be 1 minus root 3 and 1 plus root 3. 1 minus the root of 3, or y is approximately negative 0.7320508076, and y is approximately 1 plus the root of 3, 2.7320508008. Which looks reasonable to me. All right, this would be at negative 0.732, and this would be at 0.2 or 2.732. Looks good to me. You can check it with Desmos. How would you check it with Desmos? It's not one of the coordinates that are going to pop up, right? Because it automatically populates with the x and the y intercepts, right? Anytime it crosses the axes, it'll populate, but you would need to draw a line at x equals -1, right? Just like we did here, and then it would show you where it intersects. Oh, it did a small thing, and that's okay, I guess. Kind of weird. I don't really know how to work with it.
Go ahead and get rid of it.
Well, it's just different. I can do it. It's fine. It's kind of cool. I should get used to it. Just have it on the side always. But then we can't see here. I think so, right? Or just kind of like. Now it's just, whatever. We've got options. Which circle do we want to plug in? Well, first we can check our work, right? Let's start at the very beginning. Let's write this thing in. 4 is equal to x plus 2, squared, plus y minus 1 squared. Nice. That's our first circle. Then what did we do? We rewrote it as a y equals something. Now to check that we did it right, if I draw that y equals something, it should overlap it, right? Otherwise we did something wrong. And so the y y is, let's do 1 minus the root of 3. Nope. I jumped too far. Here. 1 minus the root of 4 minus bracket x plus 2 squared. Lower half of the circle. So that's got to feel good. And then the 1 plus the root is going to be the upper half of the circle. So y equals 1 plus root 4 minus x plus 2 squared. Whew. Okay, that is great news for us. So far, so good. Now I'm going to check at x equals -1. Check my work. which means, like I said, we have to draw a line at x equals -1 in order to see those intersections. You can use kind of the cursor and follow it along the line, but I find that it's really difficult. Whereas here, we can check like that. We did it. We did so good. Keep you guessing. I'll just keep this in here for what we did. Nice. Okay. I know. Okay. I'm gonna leave these for review because we're not gonna do this stuff until Thursday next week. And so we'll need to kind of review these, but I want you to try them. And most importantly, I want you to take a stab at this little guy, probably after you've done the tests, maybe not before. But an ant is heading toward a circular region of pancake batter. The ant cannot breathe while walking through the batter. The batter has a radius of 4 centimeters. The ant is going to walk from a point 6 centimeters due north of the batter's center, so above it, to a point 5 centimeters due west, so on the x-axis of the batter's center. If the ant moves at 0.8 centimeters per second, how long will it have to hold its breath? There's a lot of components there. First, you got to draw out the situation, and then there's a lot of things you'll need to solve for. We'll do it together, obviously, but I think it's worth trying it. And I have a little ant, and I gave you a grit to use. All right. If you have any questions, let me know, but we'll pick up here for review after the test. With that, I release you.